Okay, so this is the second part of the dot product, and now we're going to focus a little bit on angles, what the dot product can tell us about angles. So to begin with, let's just draw a diagram. Let's say we're given, first of all, two vectors u and v. So let me just go ahead and sketch these out in the coordinate plane. So let's say that my u is this vector, and then my v maybe looks like this. Sometimes the question that we want to ask, this has to do when, from a physics standpoint, potentially, what is the angle between the two vectors? Potentially you might have two different forces acting on an object, and you might be curious, what's the angle between those two forces, because that diminishes the total force that is acting upon an object. So the question is, what is that angle? Now, I can just give you the formula, which I'm going to do. So cosine of that angle is going to be the dot product of u and v, and then we're going to divide that number by the magnitude of u times the magnitude of v. So that looks kind of weird because there's so many lines, so I did put a little space there. Alternatively, if you want, you can put some parentheses around it, but now you're dealing with a lot of stuff around the u and the v. So it's really up to you how you want to do it. I'm going to leave it like this. You could also put a dot in between them, but then sometimes that we get mixed up with the dot product when we do that, because this is scalar multiplication on the bottom and vector multiplication on the top. So I'm just going to leave them next to each other and assume that we all know that means multiplication. Okay, so here is the formula. Now, I want to get a little philosophical for a moment in terms of math before we go on to an example. For me, math is more about deriving formulas and figuring out where stuff comes from, and kind of just messing around with formulas and seeing what happens. Whereas a more applied mathematician might feel like, well, math is taking a formula and then using it to solve problems. So there's sort of two types of math that we think about. The math where we're just coming up with formulas and deriving stuff, and then the math where we're using those formulas to actually solve problems. Most folks would probably agree that they prefer the applications of math, so taking that formula and solving a problem. But I love showing folks where this comes from and deriving how someone came up with this formula in the first place. All that being said, because I know that most folks do prefer that kind of applied math, I'm not going to show you the derivation in this video, but I will do another optional video for the end of this section where you can watch the derivation if you want and try to follow along and maybe even do it yourself. Okay, so here is the formula for finding the angle in between. Of course, to actually solve this, you'd have to take the cosine inverse of both sides, going back to trig again. So what we're going to do is use this formula in some examples. You might want to highlight that in your notes, put a star next to it just so you can easily find it. All right, so we're going to go back to a couple of vectors we used in the first problem. We're going to find the angle between, let's go back to W and V. So V was -2, -5, and W was 3, -2. Once again, writing W in component form just to kind of match V. Okay, so V and W, those are different letters than my formula, but it still works out the same way. We need their dot product, and then we need their magnitudes. So let's go ahead and determine actually, you know what we should probably do first is just write down the formula. So cosine of theta is going to be V dotted with W over, the magnitudes, I guess it wouldn't have mattered, multiplied. Okay, so let's break this down. Let's first figure out the dot product of W. It's going to be -2 times 3 V times, the dot product V times W, plus -2 times -5, which we already calculated was 4. Now we need to find the magnitude of each vector. Going back to the previous video, the magnitude is essentially the Pythagorean theorem, finding the hypotenuse. So it's going to be the square root of 29, which you could come up with the decimal approximation for, but then that might create some rounding issues later on. So let's just go ahead and leave it. And then for w, we're going to end up with the square root of 3 squared plus negative 2 squared, so the square root of 13. You'll notice over here, I technically, for the magnitude of v, I should have probably done negative 2 squared plus negative 5 squared. But I know that negative 2 squared and positive 2 squared are the same thing, so I just kind of skipped that negative part, so I wouldn't cause any issues later on. Okay, so we have all the pieces we need. We have the dot product here. We have the magnitude of v. And then we also have the magnitude of w. So let's put it all together. Cosine of theta is going to equal 4 over the square root of 29 times the square root of 13. I will use parentheses here just to show that the square roots are different. Okay, so if we plug this into a calculator, we just get cosine inverse of all of this stuff. And when we do that, I ended up with theta is approximately 78.1 degrees. And there's my answer. Keep in mind, we do know that theta could be negative as well, because we use cosine inverse. So probably we would want to just double check with a sketch of this to make sure 78.1 works. So let's go ahead and do that. 3 and negative 2 is one of my vectors. And then the other one is negative 2 and negative 5. So I can tell that this angle is not going to be some huge number. It's not going to be 300 and whatever. And that's always the case. If you do get negative 78.1 somehow, that's never going to be the answer, because if I went around the other way, we could do negative 78.1 degrees plus 360. But we really don't care about that. We just care about the smallest angle in between the two. If you didn't really follow what I was saying there, just know that once you take cosine inverse, your answer is the answer. You don't have to add 360 or anything to it. Okay. Now, sometimes what's important to find out is whether or not two vectors are parallel or what's called orthogonal. So let's go ahead and define what I mean by orthogonal here. Basically, orthogonal just means perpendicular to each other. So if I had some vector u and I have some other vector v, right, that would be a 90-degree angle in between the two. So the dot product is going to be really helpful for us here, and we're actually going to define something, because if I took, let's say this was a 90-degree angle here, and I had my two vectors. We could actually, let's just say u was the unit vector and v was that unit vector. If we do I dotted with j, we end up with 1, 0 dotted with 0, 1, which if you calculate this is actually 0. So if the two vectors are perpendicular, that means that their dot product is going to be 0. Alternatively, if I said cosine of theta was equal to 0, if you solve for theta here, cosine inverse of 0, you'll actually end up with 90 degrees. So a couple different ways to think about it. If I look at my unit vectors, that's a nice specific example for it. Or we could think about this formula we just found, cosine of theta equals u dot v. If all of this was equal to 0, then we would see that over here, cosine inverse of 0 is actually 90 degrees. So essentially, the point of all this is, you can write this part down. If u dot v equals 0, then u and v are perpendicular, except we're going to use this word orthogonal. The reason we talk about orthogonal is because later on, when you get into, say, a linear algebra course, which is after calc, you'll talk about orthogonal sets and other topics. But the point is we're not always going to be using vectors necessarily. Linear algebra starts to deal with other spaces that you can deal with. So one of those would be functions, and you can talk about orthogonal functions. And it doesn't really make sense to have perpendicular functions. So that's why we use this word orthogonal. But if you want to just think of that as perpendicular for now, that's fine. But this is a really key point here. So if u dot v equals 0, then u and v are orthogonal. Now, we talked about orthogonal. Let's go back to parallel. If the two vectors are parallel, then that means that the angle is 0. So I'm going to leave a little bit of space here for parallel. I'll come back up to that. But if the two vectors are parallel, that really means they're sort of on top of each other like this. We maybe have u and v. Then the angle is going to be 0 degrees, which means that cosine of theta should be 1, which means that u dot v over their magnitudes, their product of their magnitudes, equals 1. So really what this tells me is that the dot product should equal their magnitude product, is what I'll call it. So this here is the dot product. And let's just call this the magnitude product. That's not really a thing, but just to kind of keep things easier to write, let's call that the magnitude product. You could say the product of their magnitudes, and everyone would understand you, but the magnitude product isn't really a formal thing. So if u dot v equals their magnitude product, then u and v are parallel, so they're in the same direction. Now there's also other ways that you could go about doing this, but this is what we're going to use here, using this idea of dot product. Okay, so let's just do an example where we determine if the vectors are orthogonal, parallel, or neither one of those. Now, I didn't talk about neither, but basically if neither of these situations are true, if u dot v is not 0 and u dot v does not equal their magnitude product, then they're not parallel, right? Because that just means we have a situation where u and v are just a little bit off, like we did up here, where we found that the angle was 78.1. Okay. So let's do two examples. The first one, we'll say u equals, let's do 3, -8, and v is going to equal 16,6. Okay. So no matter what, you're always going to first find their dot product, because both definitions require the dot product. So we're going to take 3 times 16 plus -8 times 6. And if you do this out on the calculator, you end up with 48 minus 48. So you do actually get 0. So we can stop there and we can say oops, conclusion. The vectors are parallel or they are orthogonal, we would say. Great. So if you get 0, you can just stop right there. You know they're orthogonal. Okay, let's try another one. Let's do, let's say vector A equals 1/2 I hat minus 2/3 j hat. And let's say vector B equals 3I hat minus 4j hat. All right, no matter what, the first thing we're going to do is find their dot product, A dot B. So that's going to equal 1/2 times 3 plus negative 2/3 times 4. Plugging this into the calculator or using some adding and subtracting of fractions, you end up with 3/2 minus 8/3. Oops, sorry, that should have been a negative 4, plus 8/3. Common denominator would be 9 plus 16 is 25/6. So definitely they are not orthogonal, but now we need to check to see if they are parallel. So we can say, well, they're not orthogonal because that does not equal 0. So let's go ahead and find the magnitude of each now. The magnitude of A is going to be the square root of 1/2 squared plus 2/3 squared, which is the square root of 1/4 plus 4/9. We can continue this up. We end up with 9 plus 16 over 36. Which is actually, this works out really nicely. The square root of 25 is 5, and the square root of 36 is 6. And then for B, we end up with the square root of 3 squared plus 4 squared, which is really just a 3, 4, 5 triangle, so I do know that that's 5. And so then if I find the product, their magnitude product, I end up with 5/6 times 5, which actually would give me 25/6. Now you could do all this on the calculator as well. You should end up with, I believe it's about 4.167, 4 1/6 basically. And so notice that this actually matches, this equals u dot v, which we found above. So therefore we could actually conclude that the vectors are parallel in this case. Okay, so this video did go on a little bit long, but there are a couple definitions in here. The main examples you should be able to do are shown here, where we had to find that if the vectors were orthogonal, parallel, or neither, and then also just finding the angle in between.